5/6 into the fourth, that's correct, right? 5/6k to the fourth. Got the comma and everything right? I wonder if there's something with the rounding, if I should have just cut it off.
The series calculator, what's it, the decimal point for the series calculator gives you like an approximation, does it not, for the decimal? The total has like an approximation. It says it's equal to that fraction, but it's approximately that decimal.
Yeah, this is an approximation.
15, that could mess it up.
No, we need the decimal, not the fraction. And we're rounding to 9 decimal places, this goes to 10, so it should be enough. You know what, let me try, change it, we rounded this up to a 2 for the lower bound, let me try that back down to a 1. Because if you round it up to a 2, that makes it more accurate than it originally was. And this one's rounded up to a 1. That should be okay. Let me see if that changes anything. There it is. Okay. You see what just happened? Here's your interval, right? The first time I rounded this up to a 2. That brings your lower bound in. That makes it more accurate than it actually is. And we cannot compromise accuracy. Does that make sense? The lower bound you have to round down. The upper bound you have to round up. That's going to be very important, or you're going to go through the same frustration. Does that make sense? The lower bound must be rounded down. The upper bound must be rounded up. I've done this problem many times. That's the first time I've hit one that has that issue. Time is 9:33.
So for a test, so we're not going to have those calculators.
I would give you some information.
Okay.
For an exam, I would give you some information.
We're not going to have to do.
You're not going to have to use it, add up 10 terms, no. Okay, so let's just briefly look at what we did here. Part A, use the integral to find the upper bound, so we find the antiderivative of this from its upper, so we go into infinity. So we did here, I erased the work, but that was our result. That goes there. And then want to find our accuracy, so it's less than 10 to the negative third. I erased that work, but you set this expression less than 10 to the negative third, and you saw the work. That result always gets rounded up. Rounding down will compromise accuracy. Always go up on that one. And then part C, we get what we did here in part A, we have to do that for the upper. So we use n plus 1 in the lower bound. And if you do all the steps, you'll end up just replacing n here with n plus 1. And that result came down here. And now we need to use the series calculator to calculate the first 10, sum of the first 10 terms. Put in 10 for n here, that gives you the lower boundary. Sum of the first 10 terms plus put in 10 there, that gives you the upper bound. Lower bound must be rounded down to the 9th decimal place. Upper bound must be rounded up to the 9th decimal place. All right?
Can you go back to the calculator?
Yeah.
Just go back to the final. But if you rounded wrong, that's a 4 after the 1, isn't it?
That one we copy pasted.
On the 9th term?
This I copy pasted the whole thing, I didn't round this.
Oh, okay.
Yeah. And I don't know if right-click copy works.
Control
See, it does
V?
not give me a paste option. I had to do Control C and Control V. All right? I gotta tell you one more thing. So for the next problem, you're gonna have to do the antiderivative of an exponential. So you know that the antiderivative of e to the x is e to the x, right? The antiderivative of 2 to the x, what's that? No.
Oh.
It's 2 to the x over ln 2. Okay?
I need that.
Let's confirm that. Yep, see it there? Oh, you don't see it. It's right, I'm sorry. It's correct. So all you gotta remember is, e to the x, the antiderivative is itself, e to the x. Any base to the x, the antiderivative is itself, but there's a little adjustment divided by natural log of the base. Okay, it's just an adjustment you have to make. So that'll be the case. You'll have one of those in the last problem. All right? Have a great day. We're gonna move on Wednesday to section 10.5.